So when curve sketching or when graphing a function, something that we've learned from calculus that we couldn't do in our grade 12 pre-calculus was find maxes and mins. Right? If we had an x cubed graph in grade 12, you knew how it ended. You might have been able to find x-intercepts. You learned about multiplicity, about when a graph bounced off an x-intercept or when it went straight through. But you didn't know how to find those maximums and minimums. Okay? So the first thing we learned in calculus is how the first derivative can help us find these maximums and minimums because the tangent can equal 0. The next thing that we look at in calculus is concavity. Because on a graph, there are parts of your graph which are concave down, and I'll show that in this section here that's red, where the curve is down, concave down. And there are parts of the graph that are concave up, and this point right here is a point where it changes from being concave down to concave up. So knowing that point can also help us draw our graph more smoothly and more accurately as well. Okay? So we say that a graph is concave up if the curve would lie above all of its tangents. So does that make sense? The green section that I drew concave up. No matter where I draw a tangent in this section, my green curve is above it. And it's concave down when the curve lies below all of your tangents. So as far as derivatives go, your second derivative is your rate of change of your first derivative. So if we look at a section that's concave up, if it's going to stay concave up, let's look at our derivatives. What's happening to my derivatives at 0.24, then it goes to 1.7, then it goes to 4.05. Here it's concave up. My derivative starts as negative, then it's at 0, then it's at 1.63. Can you see that your derivatives are increasing? Yes. What's that? On both sides of a parabola, depending on where, like, if I had this point and this point, those slopes would be the same, but one would be positive and one would be negative, right? In this case, I have this point here and this point there. These are arbitrary points, but what we're trying to notice is that if something is concave up and we look at the tangent slopes, as you move along it, your tangent slopes are increasing. So, in the same way that we did our first derivative and found out where our graph was increasing, if we find out where our tangents are increasing, we can say that our graph is concave up in that section. In other words, if your second derivative is positive in a section, then it's concave up in that section. Because whenever you plug in something into a derivative, it tells you how things are increasing before that, in the function before that. And if our tangents are increasing, then it's telling us that our original function was concave up. Similarly, if something's concave down, then your tangents all lie above your curve, and your curve lies below your tangents. And if we look at those tangent values, they're decreasing now. So if your second derivative is less than 0, then it's concave down. So we're going to see with a couple of examples what this means. It's really easy to figure out. Okay, here we've got a section labeling the blue parts as being concave up, the red parts as being concave down. And the points P, Q, and R are where it changes from concave up to concave down, or concave down to concave up. So if we were going to give the intervals where it's concave up and concave down, -4 to 1, 3 to 6, and 6 to 8 are all the sections where it's concave up, and 1 to 3 and 8 to 9 are where it's concave down. So we learn a new definition here. We call the points where it changes concavity points of inflection. And we've seen this word before because when we did stationary points, I said you either have a stationary point is either a maximum, a minimum, or a stationary point of inflection. And I mentioned that stationary point of inflection appears only on an x, well, not only, but one example is on an x cubed graph, where at 0, 0 on x cubed, the tangent is 0, but it's not a maximum or a minimum. But if you think back to your x cubed graph, can you see that it is a point of inflection? It changes concavity from concave down to concave up at 0, 0. So at a point of inflection, the second derivative is 0, and the second derivative changes sign. We also make a note that if the second derivative is equal to 0, the first derivative can't change sign at that place. Because I can make an example where the second derivative is 0, but it happens to be a minimum or a maximum. Again, we're sort of developing the theory right now. So don't worry if you're like, I'm not quite grasping all of this yet. Once we get to a couple of examples, it's really quite straightforward and a lot very similar to the first derivative test and how we found maximums and minimums and where our graph was increasing and decreasing. Stationary points of inflection. Those are the points like in the x cubed graph. You have a stationary point of inflection where the derivative is 0. And I'll have this example off to the side. Okay, here's our x cubed graph. X cubed graph has a stationary point of inflection at 0, 0. If I find the derivative of x cubed, it's 3x squared. Can you see when you set the derivative equal to 0, x is 0. If you did your first derivative test and you plugged in 0, you would find out that it was increasing and increasing, which our x cubed graph is always increasing. Right? You plug in a value less than 0 into your derivative, it's positive. You plug in a value bigger than 0 into your derivative, it's positive. Makes sense because it's squared. So you have a stationary point of inflection when the derivative is 0 and the second derivative is equal to 0. So if I find my second derivative now, it will just be 6x, and setting your second derivative equal to 0, it's also equal to 0 at 0. So if both the first and the second derivative are 0 at a point, you have a stationary point of inflection. You could also tell it's a stationary point of inflection just from the first derivative test. If it's equal to 0 here but keeps increasing, the only possibility is a stationary point of inflection. 2, the gradient of the curve on either side of x has the same sign. So that's what we're showing right here. That if I plug in a number less than 0 and bigger than 0, it stays positive, so that makes it have a stationary point of inflection. You have a non-stationary point of inflection. The derivative is not 0, and the derivative at the point is not 0, but the second derivative is 0. Okay? And the gradient of the curve on either side still have the same sign. And we'll also find out that this shows true with plugging in values into the second derivative. You can show that it changes concavity. So we're going to look at some examples for this and come back to these ideas afterwards. So here we have x to the 4. Consider this function. Special note before we get to this. To show that a point is a point of inflection, it's not enough just to show the second derivative equals 0. That's a key thing, finding out where the second derivative is equal to 0. But you also have to show that the first derivative doesn't change sign at that point in order to show that it is a point of inflection. So here we have x to the 4. X to the 4 is like an x squared graph that's just flat. This graph has no points of inflection. When you find your first derivative, you find out that your derivative is equal to 0. When you look at your first derivative test and you plug in something less than 0, it's negative, and greater than 0, it's positive. So it's decreasing and then increasing, which you can see in the graph. Zero is not a point of inflection because it's a local minimum. One of the things that we're going to do with our second derivative is we're going to make another sign diagram and put our second derivative on there. And if I take my second derivative, what happens when you plug in something less than 0? Well, 12x squared would be positive. I like to make cyclops. There's your positive cyclops. And it's happy, so it's concave up. Plug in something bigger than 0, it's also positive. It would also be concave up. And since our graph doesn't change concavity at 0, it is not a point of inflection. Question? Do you have an eraser? I do have an eraser. Here we have an x cubed graph. From grade 12, you could quickly sketch this by taking your x cubed graph and translating it 3 to the right. So whenever we have stuff that we can use from grade 12, I'll remind you of it. Find the second derivative. There's our first derivative. And, I should find our first derivative first. This is actually our, this is the first derivative, and you have to find the second derivative. Sorry, I misread the first question. So I drew a graph of the derivative, not of the original function. Function has its first derivative, x minus 3 cubed. Find the second derivative, which just is taking the derivative of that first derivative. Find f prime of 3 and f double prime of 3. So we plug in 3 into the original equation, we get 0. We plug in 3 into the second derivative, we get 0. Since they're both 0, this is not a point of inflection. In order for it to be a point of inflection, the second derivative has to be 0 and the first derivative can't be 0. So what does this mean? If we look at our sign diagram with the first derivative, at x equals 3, it changes from decreasing to increasing. And so that means from the first derivative, it's a minimum. If something is a minimum, it doesn't change concavity. Another way that you could explain that it's not a point of inflection is you could do the second derivative. Oh, I'm going to erase these. Make my Cyclops. If you plug in values into your second derivative, they're both positive. And so it'll be concave up in both sections. And any time your graph does not change concavity, it's not a point of inflection. So with our first and second derivative, we're getting very close to being able to quite accurately graph any polynomial function. So for each of these graphs, we're going to find out where things are concave up and where things are concave down. We can look at our graphing calculator to sketch, but we can also think about how we would sketch this using calculus as well. So right now we're just concerned about where things are concave up and concave down. First of all, you know this is a parabola. Is this a parabola that opens up or opens down? Up. It opens up. So without any calculus, would you be confident to say that this is concave up always? Yes. Okay, good. But let's look at the calculus. So we find our first derivative. Then we find our second derivative. Our second derivative is just equal to 6. 6 is always positive, and there are no critical points. So if you wanted to draw your number line for second derivative, there would be no points that you would put on it. And any number that we plug in gives us 6, which is always positive, which will always be concave up. So where is it concave up? Everywhere. You could write a negative infinity to infinity, or x belongs to the real number. There are no inflection points. And we graph this on our graphing calculator. We already knew it was a parabola that opened up. So it makes sense that it's always concave up. If I had to label my minimum, can someone quickly tell me what the x-coordinate of that minimum would be? Without a calculator. Just looking at this stuff that I mean, you could type it into your calculator and tell me the minimum. 5/6. How did you find that 5/6? Yeah, I went to your first derivative and said, plug in 0 for my first derivative, because if my slope is 0, my tangent is 0, that's when I'm going to have my minimum. What's x to do that? 5/6. To find the y-coordinate, you could plug 5/6 back into your original equation. You'd have some not very fun fractions to work with, but it could be done without a calculator. Good. Something a little bit more interesting. It's a negative x cubed graph. From grade 12, a negative x cubed graph would go like this. Can you see that there are some sections that are concave up and some sections that are concave down? If we find our first derivative, we get negative 2x squared minus 8x plus 10. If we find our second derivative, we get negative 4x minus 8. When is our second derivative equal to 0? It's equal to 0 at x equals negative 2. So you would go and make your number line. I know I probably have it underneath the next slide anyways, but we make our number line, we plug in negative 2, and check what happens before negative 2. Okay? And maybe it's important to find concavity. You're plugging values into the second derivative. So if I plug in something less than negative 2 into my second derivative, say negative 5, what am I going to get? 20 minus 8, positive 12. So if I plug a number less than negative 2 into my second derivative, it comes out positive, meaning that section has to be concave up. Does that match? Yes. If you plug in the number into your first derivative, it won't tell you anything about concavity. First derivative would tell you at that point if it's increasing or decreasing. And in your first derivative, right, if I quickly factor my first derivative, I will get x minus 5x plus 1, so 5 and negative 1 would be my critical points in my first derivative. And from my first derivative, if I plugged in values into my first derivative, less than negative 1 would show that it's decreasing. Then it would get a positive number, show it's increasing, and then decreasing again. So that would be those points there and there, negative 1 and 5. But if I plug numbers into my first derivative, it just tells me where my original graph decreases and increases. Plugging numbers into my second derivative tells me where my original graph is concave up and concave down. So plugging in something larger than negative 2, like 0, into my second derivative gives me a negative number. Draw the cyclops with a negative sign, looking sad. That section will be concave down. So it's concave up from negative infinity to negative 2, and concave down from negative 2 to infinity. Oops, I had my factoring just a little bit off here. Mental math, it was negative 5 and positive 1. There we go. So your first derivative tells you maxes and mins and where a graph is increasing and decreasing. Your second derivative finds this point right here where it changes from being concave up to concave down. So what we're going to find as far as sketching is if I can find this point and I can find my maxes and minimums, I can start from my inflection point and draw a smooth curve concave up easily there and draw a smooth curve concave down easily there. And I have a really accurate shape of my graph as a result. From grade 12, what does this graph look like? It's an x to the 4 graph, and it's positive. So yes, you are right. Its end behavior acts like a parabola. It might have something interesting going on inside. We don't know if it's a perfect W or not. Right? Could look like that. I've seen ones look like this. But the end behavior is opening up like a parabola because it's a positive x to the 4 graph. Can you see that there's possibilities for changes in inflection? Right? If it was this W graph, it looks like those points are where it changes from concave down to concave up, back to concave down. If it was this second graph that I have, it looks like there it's concave up, there it's concave down, and then it's concave up again. So let's find out which of these two graphs it is, or if it's another one. Find our first derivative, find our second derivative. Our second derivative factors, and so we get x equals 0 and x equals 2. I would draw my number line with 0 and 2. Good. Where are you at? I'm almost
Get to the second derivative test.
Okay.
As far as I want to get. Where are you?
I'm just on this one here, so I'm not very far. You're right here?
Yeah, I want to get right up to there and stop.
Okay.
I'm just not feeling up to it. Trying to fade. Is that okay?
Yeah, that's fine. We are planning together because on Thursday, both my grade 12 class and Mr. LaFrance's grade 12 class are writing their provincial math exam. So my class is right in the cafeteria, and there's my class and Mr. Smith's class are both writing in there, so he can cover and I can come back and teach both classes calculus while Mr. LaFrance is covering his class, his exam there. So on Thursday, as a large group, we'll go over our tests and we'll start the second derivative test. Okay, so we've got our second derivative. We found out where it's equal to 0 and where it's equal to 2. Not where it's equal to 0, where it's equal to 0, and it's equal to 0 at 0 and 2. So we can draw our number line for the second derivative. If we want to find out where things are concave up and concave down, this note that we wrote on the last one, we plug our values into the second derivative. What happens when you plug a number less than 0 into your second derivative? It's positive. Why? Because this section would be negative, right? and something less than 0, this would be negative as well. And a negative times a negative is positive. This section is concave up. Something between 0 and 2. Plug in 1. 12 times 1, positive number. 1 minus 2, negative number. Positive times negative, negative. Concave down. And something larger than 2, this will be positive and this will be positive. It's back to concave up. So we can say it's concave down from 0 to 2 and concave up from negative infinity to 0 or from 2 to infinity. Did you know that this U thing in mathematics means or? So it's telling us it's concave up in this section or in this section. We don't use the word and, because the word and says it has to be in both sections at the same time.
Isn't that like in probability?
Did we use the union sign in probability? Yeah, when we did the Venn diagrams, right? Now, if we graph this on our graphing calculator, it ends up looking like that second one. It changes concavity at 0, 0. And it changes concavity at -2, -16. If I wanted to find those y coordinates on my original graph, you always find coordinates on your original graph by plugging them into your original equation. Just for fun, well, I mean, this has all been fun so far, but if we look at our first derivative and you set your first derivative equal to 0, can you see that you could factor out a 4x squared? If I factored out a 4x squared, I'd be left with x minus 3. When is my first derivative equal to 0? At x equals 0 and x equals 3. If you made your first derivative number line and plug things into your first derivative, you would find out that less than 0, this section is positive, this section is negative. Positive times negative means your original function is decreasing before 0, which we can see on our graph. It goes down to 0, 0. And then between 0 and 3, if you plugged in 2, this is still positive, this is still negative. It's still decreasing. Okay? That decrease tells us at 0 we have a stationary point of inflection. It's not a minimum or a maximum because it didn't change from decreasing to increasing. But at 3, when you plug in something larger than 3, this section is positive again. So we know that at this point, 3 comma something, we have a local minimum. So looking at our graph, we know that it's decreasing, decreasing, and then increasing afterwards. From grade 12, oh, I love making all the connections, okay? From grade 12, you already told me you knew the shape of it looked like this. Something else from grade 12. From grade 12, you could find the x-intercepts. How do you find x-intercepts? You make y equal to 0. How would you solve where this is 0? Could you factor it? Yes, there's a common factor of x cubed that comes out, which would tell you that you have an x-intercept at 4, 0, and you had an x-intercept at 0, 0. But the x-intercept at 0. In grade 12, we said this had a multiplicity of 3. And what did that multiplicity of 3 mean for a graph? Right? It looked, I described it to my class that it still went through, but it bent. Right? Sometimes your x-intercepts bounced off like a parabola, and sometimes they bent like an x cubed. So this multiplicity of 3 told us that right here, it needed to bend. How do we see the bend now in calculus? We see the bend because of an inflection point. And the only way you can, if you draw a point and you want to draw this side concave up and this side concave down, the only way to do that is to get that bend in the graph. So all of these ideas start to come together. And we see some of the things we saw in grade 12 that were just starting to get our curve sketching. Now the calculus is filling in all the missing things that we had from before. Why that bend is there. Where our maximum and minimums are. And in grade 12, you memorize that it's x to the 4, so its shape is like this. Now with decreasing, decreasing, increasing, you know where the end behavior has to be from calculus. Two x e to the x. We did not graph this at all in grade 12 pre-calculus. We graphed e to the x by itself. We graphed 2 times x by itself way back in grade 10, maybe even grade 9. But putting those two together, no. So we find our first derivative. And with the first derivative, simplified it by factoring out a common factor. Found the second derivative using the product rule again. Can set our second derivative equal to 0 and simplify a little bit of algebra needed to be done, but not too bad. Again, the idea of a common factor comes into play. So can you see from this step to this step that we noticed there was a common factor in each of the 3 terms of 2e to the x? So I factored that out in front. And once your equation is factored and simplified, then when you set your second derivative equal to 0, this factor is easy to make equal to 0. X equals -2. 2e to the x, you have to think back to grade 12 and say, I know what my e to the x graph looks like. My e to the x graph is an increasing function with an asymptote at y equals 0. Is my e to the x graph ever equal to 0? No, because there's an asymptote. It is, in fact, never 0, and also, from that graph, we can also say it's always positive. So knowing the properties of a function can sometimes best be remembered by saying, I know what the graph looks like. And because I know what the graph of e to the x looks like, I know it never equals 0, and it's always positive. that's going to become important because now when I plug in to my number line something less than -2, like 0. No, 0 is not less than -2. Like -3. If I plug in -3, this is always positive. But -3 would make this section negative. I can put a positive here because I know that is always positive. Positive times a negative makes this section negative. Sad concave down. Plugging in something bigger than -2, like 5, makes this section positive as well, telling us this section is positive. So we know that at -2, there's an inflection point. For curve sketching on this one, plugging in -2 into your equation, into your original equation, would give you -4e to the -2. So this value right here is -4e to the -2. If you wanted to write it as an exact value, perfect. Although, if you're trying to graph this accurately on graph paper, plugging in the point -4e to the -2 is not something that's easy to say, oh yeah, I'm really good at estimating where that is. Okay? So you would need to go to your calculator to figure out that that value is -0.5-ish, written there to 3 sig figs to get it more accurate. This is the shape of this graph. It's an interesting graph because it has an asymptote, but your graph goes through your asymptote. It has a horizontal asymptote at y = 0. And we remember that horizontal asymptotes are there to tell us what happens at extremes. And as x goes to -infinity, it approaches this asymptote. We could even perhaps draw it as a partial asymptote because it only shows what happens to the extreme when it goes to big negative numbers. Can you think about that limit as x goes to -infinity? Does that make sense? In our original equation, right here, if x is a very, very large negative number, what happens? Okay? 2 to the -x gets really, really big, and e to the -x, or e to the x, would become e1 over e to the positive exponent, would become very, very close to 0. And in calculus, in limits, and we don't go to it in too much depth here, but you will more in university, and we'll do it a little bit more if you're in the advanced math calculus course. What we have here is the limit as x goes to -infinity of 2x e to the x. This part goes to -infinity. This part goes to 0. And in mathematics, infinity times 0 ends up being interesting sometimes. In this situation, it ended up being 0. In other situations, it's going to end up being infinity. It just depends which is more powerful. And certain functions are more powerful than other functions. Okay? For example, if you were making money and x was getting bigger, which function would you pick? A line, 5x plus 3. So put in $100, you get 5 times 100 plus 3, $503. Good deal, like it. Or would you pick a squared, x squared plus 2, which would make you more money when you put in a bigger number, x squared, rather than x. So we say that x squared is more powerful than x. Here we have a line, which is 2x, and we have e to the x. Which is more powerful? Putting 100 and timesing it by 2, or putting 100 in as an exponent? The 100 as the exponent is more powerful, makes things increase or decrease faster. So in this situation, the 0 is more powerful than the negative infinity. And for that reason, this is hand-waving reasons. We'll get into more in-depth mathematical reasons later. But this is the hand-waving idea of why at infinity it goes to 0. Because the 0 is more powerful than the negative infinity. Oh wait, but that's, sorry, getting a little off topic. This is where we're going to end for today. And what we're going to do for rest of class